Welcome everyone, my name is Cameron Riddell and I'll be today's lead presenter for what you won't learn on Stack Overflow when talking about NumPy and pandas. I have spent countless hours answering hundreds of Python questions on Stack Overflow and know that most people come in with pointed questions and receive pointed answers. You'll see a lot of questions with some very specific snippet of code and then they just get an answer that says, try this, and then it just happens to work, right? And then you'll find that answer and you'll do the same thing, you copy and paste some code into your own program. As a result of this incentivization system that Stack Overflow has, you're more likely to stumble across these answers than those really great, filled out, conceptually complete answers that don't assess why there's this misunderstanding or this question in the first place, but simply to get those sweet internet points. Today, I'm here to show you these fundamental ideas, these core concepts of both NumPy and pandas that will help orient your thinking and set you right in terms of how to approach these packages and how to apply them in your own work. With this understanding in your tool belt, you'll be able to very readily apply these concepts and stay away from Stack Overflow yourself, since you'll be able to answer a lot of your own questions. That being said, I think Stack Overflow is still a fantastic resource and a great place to get help if you have any specific questions. With all of that being said, I'm excited to get started, so let's dive right in. You'll see my code behind me. I'll hide here in the corner, and we'll go ahead and get started. In our first question, what is the point of vectorization? We'll discuss some of the core ideas as to why do we even need NumPy, or why do we need pandas in the first place? What's wrong with just pure Python? So, let's get started. If we were to just create a simple Python list containing the values 0, 1, and 2, we can apply mathematical operations to this list. If I wanted to multiply everything by 10, I can do that quite readily. I need to use some type of looping mechanism, either a for loop or a list comprehension here, and I need to specifically operate on each element in a very explicit manner. Now I can even do things in pure Python that are more on the statistical side or more on the advanced mathematical side, if you will. I can, let's say, import something from the statistics library and I can calculate the mean and I can calculate the standard deviation. I can use these values to normalize my data or to z-transform it. However, you have to be careful with this line of thinking or with this approach, because actually in this snippet of code you'll see here that for every item in x's, I'm actually recalculating the mean and recalculating that standard deviation, which is something I want to stay away from, especially when I'm dealing with, let's say, a lot of data. Instead, what I'll want to do is actually pre-calculate these values, and then I can apply my list comprehension to iterate on things and subtract my mean, divide by standard deviation in order to normalize my data. And if you really dislike your coworkers, you can do something like this, where you're checking the state of the globals in order to kind of sidestep some of this repeated computation and keep everything inside of your list comprehension. Additionally, with pure Python, you can very well add two arrays. But something that is interesting that arises. If you use kind of the intuitive approach, right? If I want to add two lists together and I simply use the addition operator, I'm actually concatenating these two lists, which is a very interesting point that I'll save just for a moment here. If I actually wanted to add the values within these two lists together, I would have to zip them together in order to operate on the elements of that list at the same time. And what you see here is this repeated idea that if I want to do anything in pure Python that's mathematical, or if I want to operate on any of the elements within a pure Python container, I need to explicitly iterate over it. And this is what the first kind of idea of vectorization gets us. We'll see in a moment that vectorization abstracts some of this explicit looping away, tucks it under the hood, so that we can operate on the elements of a container without really acknowledging the existence of that container. But in order to differentiate pure Python from NumPy, we need to understand that these two objects, these two package or base Python and NumPy, really are set out to do two different goals. If we examine the operations in NumPy and examine operations on pure Python containers, we'll note a dichotomy. And that is that the NumPy operations work on the elements within their container, whereas the pure Python operations on a list or a tuple or a set, a dictionary, right? All of our base data structures do work on the container itself. And so if we just examine the methods and the attributes that come from a Python list here and a NumPy container or a NumPy ND array here, we can see that the list has append, right? Add an element to the list. That's a container operation. Clear. We're deleting everything from the list, another container operation. Copy, we're going to copy everything from the container. And so on and so forth. Whereas our NumPy ND array has methods like all or any, right? It's examining the contents of the container in order to make some assessment or make some determination about it. Argmax or argmin, find the position of the maximum value within the container. And so we'll see this kind of dichotomy. And going back to our previous example, right, this idea is why I can't just add the elements of two lists together, right, just by using the add operator. Because the lists operations work on the container itself and not its elements. And this gets into our idea of vectorization, where we can use vectorization to abstract away the for loops, the explicit looping, and that is one of the strengths of vectorization. We push these loops somewhere else in order to express ourselves in terms of operations on the elements within the container. And so you see here, if I have a NumPy array, if I wanted to add 5 to everything in that NumPy array, I simply write x's plus 5. And this is smart enough to know that I'm not trying to add 5 to the container, but I'm trying to add 5 mathematically, right, to every element in it. This gets us a little bit closer with true mathematical notation, as well as getting rid of the explicit for loop, so that I can write more succinct, compact mathematical or numerical code without having to worry about all the messiness that comes in with looping. You can think if this data structure were nested at any level, that's another layer of looping that I'd have to explicitly write, and all of a sudden my mathematical computations would be more about writing Python loops than they would be about actually performing computations. And so that's one of the strengths that we gain from vectorization. But I hope you're also thinking, well, vectorization is a little bit more than just abstracting away for loops, right? When we think of vectorization, we often think of fast computations, right? And we all know that Python is quite slow. But I can abstract for loops away in Python, no problem. And what you can see here is that I can inherit from the list itself. I can override the addition operator, and I can use this as a pure Python container, right? I can just write x's plus and then some other list, and this is now performing an element-wise addition. I can also implement my own type of broadcasting, where I can write x's plus 30 and implement my own broadcasted version. What's wrong with this? Well, nothing's wrong with this, and I think there are some people who would argue that this is a vectorized operation. But the definition does get a little fuzzy when we're talking about high-level programming languages like Python. The most standard definition that we get in terms of these, within the context of higher-level programming languages, is that we're not just abstracting for loops away, right? We're not tucking them into some function or some class or some method. We're actually pushing them into what we like to call the restricted computation domain. We're pushing the looping away, not to be done in Python, but in a lower level language, C or C++, whatever our packages have been written in the case of NumPy, it's usually C. And so what you get here is our very fast mathematical operations, and also you receive that lack of explicit looping. And so if I were to time these two operations where I am generating, right, a NumPy array of 10,000 numbers and a Python list of 10,000 numbers, and I simply time, right, how fast is it to add 1 to each of those values in the NumPy array and write a little explicit loop list comprehension here to time the Python version, we'll note that the NumPy version ends up being quite faster. And so that is the point of vectorization. We are abstracting for loops away. We are pushing them down into the package we're working with, into NumPy, into pandas, so that it can perform these operations fast and succinctly. And we gain the added benefit of working with a much less verbose yet more expressive language to express our mathematical computations within our program. And that is what vectorization in Python is all about, and that's what you won't learn on Stack Overflow.